Is, picture's worth 1,000 words. It's flip that switch back and forth, and I could generate DC, right? You understand? But I'm gonna have to be really good, and I'm gonna have to be really fast. The motor is turning. Why don't you let the motor constantly do what? Switching. So even on DC motors, I'm putting DC on a motor, yet when it starts spinning, it's trying to give me what? AC, right? You understand? So we got to have the ability to take DC into something that's in motion that's trying to do AC all the time. Huh? No, the dotted lines on your meter is called an analog scale. The problem with digital is very slow. It's just like me coming up here and putting a base up here, base 10. I said, okay, everybody, take that base 10 number and convert it to binary. Can you do it instantly? No, it takes time. So the quantities I'm measuring are analog. My meter is digital. So it's got to go through A to D conversion. But guys, A to D conversion takes what? Time. So that's why your digital meters have problems keeping up with things that's changing real fast. So the advantage of an analog meter, by George, if it's got something doing this, your little analog meter will do that, right? Your digital meter might jump all over the place because it's trying to catch up and it never can catch up. So a lot of your meters will put an analog scale on there. And it's a line that does what? That moves. What we do on the generator is we come over here and have an assembly on the back called a commutator. And y'all learned this in motor control because we talked about DC motors and motor controls. And the generator has to have exactly the same feature. So what we do on the motor, on the generator, is we come over here and we have these things like this. And we have more than this, guys. This would be a pretty bad DC. So the more sections you put in your commutator, the smoother the DC gets out. And then we'll mount a brush. And then we come over here and we turn the tag generator. Well, it don't make any difference which lead on the north side. When it's up here, it's on the north side, it's going to output a current, right? And it's going to go in one direction. So what we're doing is we're constantly swapping the north and the south coming off of the motor or the generator. But we're letting the what? We're letting the generator do it itself. So what I'm going to do, is I'm going to pass this around. And I'm going to let you look into this and actually see the commutator inside this DC generator or DC motor. So we call them segments. And you'll have to look right back in here. So we have to have brushes, right? You understand? And then you can look down here and you can actually see the slot. If you look down right in here, in fact, you can almost see it on the camera. Can you see the little segments come back? So what we're doing is the motor itself is constantly switching the output of that generator, making me get what out of there? DC. And the more segments you have on your commutator, the smoother the DC will be. But that's going to be more coils that you got to wire because each set of coils are wired to its own commutator segment. So we have to have brushes. We have to have a commutator, right? You understand? So what problem do we have with DC tag generators? What do you think we got to do with these things? What's these brushes going to do? They're going to wear out, right? You understand? So we got to maintain these brushes. While they're wearing, that carbon off there gets inside your commutator segments and eventually would short out your commutator segment. So we got to keep the commutator clean. So these guys require periodic maintenance. If you don't do periodic maintenance on them, then they're going to do what? They're going to fail. Everybody okay? So you ever see these? They've got little slots on the side. They got holes. They got screws on, so you can come through and you can screw and take the brushes out. And then you can access the commutator. You spin the motor. You have a special. It's a little rock. It's on the end of a rod, kind of like not a file, but it's gritty, and you use that to clean the commutator. And you got to do that. If you don't do that, eventually these guys are going to fail. The commutator or the brushes are going to fail. It's just like every alternator on your car does what? Fail. We were going down to. I had a big Dodge van. and we were going down to Gulf Shores, and the alternator went on the way out down there. I pulled the brushes out of it and noticed they were all worn out. How much does an alternator cost? Coming back, I went by an auto place. They had the brushes there. It cost me $2. I changed the brushes out in the alternator and drove home. Most people don't know that. So their alternator goes out.
You did that before your battery run down.
No, my battery was dead, but luckily we were with somebody. We was going down, we was carrying a lot of guys down going deep sea fishing. And so we had two vehicles. What was fun though was trying to get everybody out of my big van into this other van. We was all sitting on the floor laying on top of each other. But we was only about an hour out of Gulf Shores at the time. So I left my van at one of the rest stops. We stopped and asked her there. And, while I was there, I pulled the brushes out. Luckily, it was accessible, and one of them was wore out. So I fixed my van for $2. On the way back, they stopped. I put the brushes in there, jumped me off, and we drove the rest way home. So, and how many? And if you knew how to do that, normally what you do is they give you a core charge. You take your alternator in there and you give it to those guys, right? They send it down to like Chancey's alternators down there in Bessemer. Goes in there and changes the brushes out, sells them used for $100 again. You know, $2 worth of parts make $100. And how much they give you on your trade-in? Yeah. I know on your car battery, they usually give you $5 for your core on your car battery. Then they'll take it and they'll drain it and clean it out and put new acid in it. And if it's still, then they'll go down and that guy down on 15th Street down there in Bessemer. What's he call himself? He sells used batteries. Yeah, he's right there, right there by the interstate, right by the property. Huh? It depends on where you got access to it or not. Some of them make it a little easier. Luckily, mine had access to the brushes. This was an older type unit. I wouldn't do that now. I just don't even use it. Yeah, I would. That's the difference with the full battery. But you, the slip rings on an alternator are usually mounted in the back. So the slip rings on an alternator, what they do, if you looked at the back of the rotor on the alternator, it's got 2 rings on it. But instead of being around the outside like the commutator is, they're on the back of the alternator, like this. And then you have 2 of them. And then the brushes are mounted from the back of the alternator. And if you see 2 slots in there, 2 screws, then odds are you can do what? You can pull those brushes out. These you don't have to worry about cleaning as much because they don't have those slots in them like we do on DC. So the problem with DC generators is this gap right here. This is insulated in those slots. And you got those brushes, they're made out of carbon, right? You understand? And when they wear, that carbon can get in between the slots on your, between your combinator segments. You can literally short it out. So you need to come back and clean it every once in a while. Did I pass it? Okay, so y'all can come out. Now one of them's a motor, one of them's a generator. But what's nice about DC motors, you can also use them as generators. I found that out when I was in the service. We had a Learjet that belonged, and I worked on airplanes that landed at our, and the generator wasn't working. And we figured out that the starter on it and the generator was what? The same thing.
You know, when you say generator, I think about.
What's that? It all depends. If they change the brushes out, you still have a limited life because when the brushes wear out, usually what happens is the mount for the brushes gets into the slip rings of the commutator and it'll start wearing them out. So what happens? You save a lot of money if you buy a used one, but usually it won't last as long as a lot. Usually it lasts long enough for you to trade the car in. If I was going to trade my car in, I would definitely put a used one in there.
I've changed out brushes, rectifier bridges, bearings.
Yeah, what they do in your car is they don't. Used to we had in technically generators are generators. We have AC generators and we have DC generators. So generators, AC generator has slip rings. It does not have commutators because we want AC and we get AC out of it. So originally the generators on automobiles were DC generators. When semiconductors got a lot better and we came up with these things called rectifier diodes where we could take AC and we convert it to DC, AC generators are a lot less expensive and they don't require as much maintenance. So what we did is we went to AC generators on your car. But the problem is people call them generators and they don't understand generators, so they changed the name on cars to what? Alternators. But what we do with that is that we alternate it and then we run it through rectifier bridges to turn it into DC. An advantage of AC generator over DC generator is it takes a lot less maintenance. Even though you do still have the slip rings in there, you don't have the commutator, right? You understand that? You still have brushes, but those brushes are not constantly going over that gap. So you can actually see the gap in the commutator. So when those brushes slide over that gap, every time it's going to peel a little bit of what? A little bit of the brush off. So the brushes last longer than an AC generator. But you still require preventive maintenance on any generator if you wanted to make them last forever. So an AC jack generator, so this is a servo motor right here. And this has an AC pack generator in it, built into it. So I think these two right here, I need to find some wires. I think these two right here are the motor, I think, or these two. These two are the motor. And these two are from the TAC generator. So this is a servo motor. So not only do we have the control, it has an internal feedback built into it. Now, what this is AC. But what can I do with AC that I can't do with DC? I can measure the frequency, right? So I could take that AC coming out and I can turn it into a pulse real easy, real fast. And then we could count those pulses to get a relationship to speed. So this came off of an old floppy disk drive. We don't use it much anymore. So we had to when we recorded information on that disk, it had to run at a precise speed, right? You understand? So what they did, of course, is they used the TAC generator with feedback, and they would set that as speed. I don't remember what speed it was. It was like 300 RPM, I think. It was so neat. I wish I had one around here, but you you calibrated it under fluorescent lights. So what it had a strobe wheel on the bottom of it, and then you had a little adjustment, and you'd flip the drive over, and you'd adjust the speed until the strobe looked like it was stationary. Because these lights right here are blinking at 120 times a second, right? You understand? So we could use a strobe effect off those. You'd see people trying to adjust it on incandescent lights, and they said, something's not working. So you had to adjust the speed on the fluorescent lights. Well, they went through several attritions. When they originally came out, they were 8-inch. We had 8-inch floppy disks. And what they did, they work on the exact same principle as tape drives do, except that information is recorded in a circle. And what we would do is we would step it we call them tracks, one at a time, and we still use those things. Then what they did is the magnetics got better, and how we coded it got better, and they could put more density on a smaller amount of space. So then we came out with a 5 1/4 inch floppy disk. Then the magnetics got a lot better, the read-write heads got a lot smaller. Then we went to a 3 1/2 inch floppy disk, and that was the smallest that we went to. Because what is now our preferred method of transferable data? We have flash drives and thumb drives. So the invention of flash drives and thumb drives wiped out the floppy drives. We got an 8-inch drive around here somewhere. This is a 5 1/4 inch drive.
I was going to bring in the floppy.
This guy, by the way, uses a a variation of the variable reluctance to get speed. So this is what we call a brushless DC motor. So what they do is the rotor is actually a permanent magnet. It's in a loop. And then they electronically switch these. So a brushless DC motor is controlled by electronics. We don't control it with a voltage. We control it with electronics. So what the electronics does is it switches that field around this thing. And what's going to happen is this guy here is just going to follow the field, right? Well, this magnet, this is the speed sensor right here. So when this thing here spins, this acts like the secondary of a generator, and it induces a voltage into this right here that is proportional to what? Speed. So that's the way they sense the speed on these. I've seen them use Hall effect sensors, where they'll have a Hall effect sensor mounted inside here looking at this to sense speed. This is what we finally went to, this guy right here. So this is called a brushless DC motor. And brushless DC motors have to be controlled electronically, right? What's nice about a brushless DC motor, it does not generate. So you think about the DC motors switching. And if you ever looked at a DC motor or DC generator, you're going to see arcing. You're going to see arcing at the commutator. You just can't avoid that because it's constantly going across that gap, right? You understand? If you see arcing, the first radio transmitters that we had were called spark gap generators. So the way they sent stuff is they did it just like a spark plug. They arced across a gap and it sends out these frequencies all over the place. So that was the first communication method. So these DC brushed motors are extremely generate a lot of electromagnetic interference. A brushless DC motor basically doesn't generate any. So you're going to find brushless DC motors used in any application where EMI is going to be a big problem. So any fan motor that you have inside your computer, inside your laptop, or anything like that you have is going to be a what type of motor? It's going to be a brushless DC motor. What they do is they electronically switch the field. So a regular DC motor mechanically switches the field, right? You understand that? Or a DC generator. A brushless DC motor electronically switches the field. But that's the speed sensor. So the speed sensor is actually a generator, right? You understand? It's an AC generator. So when that thing's spinning, those coils down on the bottom, it's inducing a voltage into that generator, and the voltage they've sent out is proportional to what? To the speed. Or the pulses too. So it's giving pulses too. What's nice about an AC tach is we can use one or two things. We can use the voltage or we can use the frequency. The frequency would be directly proportional to the what? To the speed. I don't want to take any of my wires. So if we're going to look at this thing, we'll have to look at it with an oscilloscope. I got some solid straight wires on that I can use for reads on the resistor. So I think this right here is the motor. It's going to be touchy to keep it in a short circuit. This is one of those don't do this at home, right? Oh, I'm off. Okay, so that's the motor. And then what we'll have to do to see this, we'll have to look at our oscilloscope to see this. So I'm going to get a couple more resistors, get my oscilloscope. sure it's working. This is one of the things I learned a long time ago. Is just touch it with your finger to see if you're, because it's picking me up. So I'm 60 cycles, right? And then we'll come over here. Oh, that one's a lot better. That bigger lead. And then what we're going to do is we're going to use our oscilloscope to look at the output of our AC TAC generators. Ah! Still working. Nothing shorted out. So if I increase this, notice we get two things that's happening. What's the two things that's happening? So not only does your frequency go up, but also your amplitude goes up. So I can use the frequency, and the frequency, by the way, would be very easy to convert to digital. Very easy to take the output of this and convert it to digital. So I can use one or two things. Best in a PLC, I would rather prefer frequency, right? If we use frequency, then we can go to speed real easy. Very little math. If I was running into some other type of control, then we could rectify this and turn it into DC, and then the DC level would be proportional to speed. So this is a servo motor. Now what's the difference between a regular motor and a servo motor? Yeah, servo provides feedback. Here, this servo motor gives us speed. Doesn't give us position, it gives us speed. So all I'm doing is changing the speed of the motor. So notice if they get closer together, it means it's going faster. If they get wider apart, it means it's going slower. And of course, that's as slow as I can go. Yeah, I don't know what the motor is rated at. So for us to do the speed, what would we need to know? We need to know the number of cycles we get per revolution. And once we knew the number of cycles we get per revolution, then we could calculate the speed. I don't know if this gives us 1 cycle per revolution or not. If it's 1 cycle per revolution, that would be nice. Because we wouldn't have to divide it by the number of encoder slots, right? Okay. Any questions on that? So we looked at variable reluctance, Hall effect, DC TAC generators, and AC TAC generators. You don't have any questions? This is a true what? This is a true servo motor. So if it's not a servo motor and we want to do a closed loop system, then we got to hook up an external sensor, right? If it is a servo motor, that means the actual sensors are built into the motor. Yeah, this is the motor. This is the sensor. No, the yellow. Yes. I don't have any tape to put on. No, the yellow green is the sensor. The yellow green is the sensor. The blue red is the motor. No, the closer the lines are, the faster it's going, because the frequency is going up. So if this is time, the closer they get, time is going down, which means if time is going down, then the speed of the motor must be going what? Up. So we can measure the time, but it wouldn't mean nothing unless we know how many cycles we get per revolution. Right? And I don't know if I could do that. Yeah, it'd be real hard. Looks like it might be 1. So this is me turning it, making it generate. So now I'm not running the motor. I'm spinning it with my hand. Now this, what they're doing is they're spinning a permanent magnet, and then they're taking the AC off the stator. So there's no brushes involved on the TAC generator. So what's nice about a TAC generator is we can do what? We can use the permanent. So on TAC generators, we don't adjust the strength of the field. We use permanent magnets. Because that way we know the concentration of the field, right? You understand that? And so what they do is they spin the field. on a AC tech generator. On a DC tech generator, you can't spin the field. You understand? Because we got to use the mechanics of the to actually do the switching for it. So a DC tech generator, you got to have brushes. An AC tech generator doesn't have brushes. And if it don't have brushes, it means it's going to last a long time. Huh? Yeah, on AC, what we're doing is we're spinning the magnet. So the rotor is a permanent magnet. So on an AC generator, the rotor is a permanent magnet and it's cutting the field. And it's permanently wound. So on an AC tech generator, there are no brushes. A DC tech generator, what we're doing is the field is stationary. The magnetic field is stationary, right? You understand? And then we're spinning something through there. So on an DC tech generator, the stator would be the permanent magnet, and then the generator would actually be in the center, would be the armature. And how do we switch it? Well, we let the mechanics of the thing switch it. So the advantage of an AC tech generator over a DC tech generator is it has no brushes. So an AC tech generator would last forever until the bearings gave out, right? Which would be it would be on the range of an optical generator. But the problem, what's nice about this is we don't have to really worry about that much cleanliness in the system, right? You understand? We can run these in very dirty environments. If it's an optical tech generator, then we're going to have to seal that thing up really nice to keep garbage out of it. The robots use optical, by the way, because here we can't get the mechanical coils. The coils we can't get them close enough together to get a high resolution. You understand what I'm saying? Because they're wire. Optics, though, we can get those lines extremely close together, and that's why I brought this up. Y'all can hear it now. That's why I brought this printer in here. I'm gonna pause this. Let's see that.